question, you can just raise your hand. How do I see? Okay. Yeah. I don't see any hands raising yet.
Yes.
Oh, okay. You can speak up.
Yeah. So, well, first of all, just to check, what was the frequency that you're doing these measurements at?
Oh, they range typically kilohertz or 10 kilohertz. I may have a slide that shows, but it's over in the electrons near 1/5, where we have much more data than these other cases. If I remember, it's yeah, here I can show you this. Right. So this is near 1/5. This is the trace, and these are the temperature dependencies. So in this case, it's 137 hertz, for example, to 19 kilohertz. So the shape of these changes, but overall, they pretty much all show that minimum and at the same place.
So to the extent that this is really low frequency, you should be primarily measuring something like a compressibility. And I suppose it's the fact that you have a very, I would say that there's sort of like a very high compressibility close to the melting temperature, which is a little bit reminiscent of a two-phase. I mean, obviously, if you have something like a mixture of ice and water, it's very compressible. Now, these have long range for it. It's not clear that this is what's going on. I haven't thought about this before. This is new. I hadn't realized this. It's very, very interesting, but extremely interesting data. But it may well have something to do with that it's a compressibility maximum that you're seeing.
Right. Yeah. Yeah. Thanks. Yeah. That's what we have thought about too. In fact, maybe I've mentioned it in the paper, but I would love to see a little more quantitative if it's possible with the theory. Yeah, that would be very nice. Thanks. Yeah.
Okay, Gabor, you have a question?
So I was just wondering, Mansour, did you have a chance to analyze your data at filling factor 1/2? Do you see any signature in this current in the stripe phase?
Near 1/2?
Or, you know, 9/2?
Or 9/2.
Yes,
and see a signal. What do you mean by signal exactly?
I mean,
so I can show you.
I may not expect a dip like you see it in the bubble, but do you see any kind of, so if you scan in the stripe phase and you measure this current as a function of temperature, your penetration current, is that flat or do you see any kind of blips in the data?
I believe it's pretty flat, but okay, let me show you this. So first, this is the transport and this IP side by side so that you can see. So this is the reentrant integer quantum Hall state. And that's where we see the maximum, right? So first here, this is what we see. It's a strange behavior to me, but it's pretty flat here. Right, and then your question is, how would this behave as a function of temperature? Is that correct? Yeah. So if I look here, as we go close to this, we lose that minimum, if you wish. In other words, our cryostat in these measurements doesn't go much below 60, 70 millik around here. Actually, it's a little lower, I guess. This is maybe no, around that, right? So we lose the minimum. You see what I mean?
Yeah.
So we can't go close. So if one could go to much lower temperatures, maybe one could continue. But my guess is there would be nothing there. This is kind of what it suggests.
Yeah, well, I'm thinking is that the stripe phase has an onset temperature which is pretty similar to that of the bubble. So at your lower temperature, you already have the stripes developed. So it would be interesting at the onset of the stripe phase if there is any signature in your penetration current. So basically around, between 100 and 200 millikelvin, I don't know, maybe you're not gonna see anything. Maybe these stripes kind of short out all to your contacts and that you're not gonna see anything, but
Right. No, I think the
Yes.
answer is, Gabor, that I don't think we see anything. I mean, again,
Okay.
here is the example, right? If we get closer, at least in that temperature range,
Mhm.
you know, we don't see anything non-monotonic, you know, showing
Uh-huh.
a minimum. But I could check with Kevin. You know,
Okay,
Kevin.
thank you. Mansour.
Sure.
Okay, Song Yang, you have a question?
Hi, hello. I have a question for Professor Shayegan about the regular crystal part. So,
Yes.
Is that possible that near the melting temperature, before the electron regular crystal translate to the fractional quantum Hall state, it first translate to a regular crystal state of complete fermions, and the regular crystal state of complete fermions has better screening effect than electron crystal, so that causes the phenomena we see.
Oh, sure. I mean, in the experiments, I'm not sure how we could, you know, give a definitive answer. But if there is some intermediate phase or, you know, intermediate species that are melting, yes, it could be. I mean, do you know roughly the temperature range or what one would expect such things?
No, that's just a board guess. I don't know.
Right. Yeah. So you can see here. So what we see is this comes down and goes up. You know, if you had some clear evidence from, say, calculations or some other measurement that there are composite fermions involved, and that's why it's different. Sure, it could be.
Okay, Dan Song.
Thank you.
Dan Song, you have a question?
Yeah. I want to ask Inti Sodemann about his is the Landau damping this sigma transfers independent of the Landau parameter?
Yeah.
Yes.
So basically what we showed is that it's independent of the Landau parameters and the quasi-particle mass, the quasi-particle mass and the Landau parameters. And you need to be, you know, if you have collisions, then you need to be at some Q that is larger than the inverse collision length. So you need to be sort of in the clean limit, let's say. But it's independent of Landau parameters.
Very interesting. Thank you.
Thanks.
Okay, Stephen, you have a question?
Yeah, another question for Inti. I was wondering if you kept the long-range Coulomb interaction in your in deriving this criterion that M is 2M0 or M is 6M0 for the getting an independent shear mode, because if you include it, it's like having a divergent F naught as you go to Q equals 0, and that still leaves the criterion unchanged.
Yes, so this criterion is derived in a description in which you only have F0 and F1. Okay, so the criterion will be slightly different if you have, let's say, you know, higher F2, for example. It doesn't change very much. We have some numerics of how it changes with having, let's say, finite F2. It's roughly, you know, doesn't have any very dramatic change. But F0 does not enter. So when you add the Coulomb interaction, it doesn't change the criterion.
Thank you.
Because it's purely shear, right? So there's no density fluctuations.
Right.
So it's purely shear mode. So the F0 part does not enter into the calculations.
And if I can add just one other question. I mean, do you also get higher modes, F2 modes, F3 modes, and so forth?
Yeah.
Those can show up also.
Yeah, so, you know, as you can cap the other Landau parameters, you will get other modes. This is, let's say, the simplest, you know, strange mode that you would get out of anything you could get, let's say.
Thank you.
Thank you.
Okay, Janendra. you have a question?
Yes, I do. So this is also a question of Inti. So for your latter part of your talk, when you talked about spin charge separation and spin-on Fermi surface and so on, are you trying to describe what would happen if there was spin charge separation, or are you actually saying that there would be spin charge separation in certain parameter regime?
Yeah, so the description is basically assuming the spin-on Fermi surface state is there.
Okay.
Right. What would be its behavior?
Okay.
So we use essentially a field theory, right, of the spin-on Fermi surface that is meant to be just a low energy, long wavelength description. So the universal property, I believe to be a property of that phase of matter.
Okay.
So if you're in that phase of matter, in that particular limit of omega and q, you will get this universal response that is independent of all details other than the shape of a Fermi surface of the spin-ons. That's my belief.
Okay, thank you.
Yeah, thanks.
Okay, Doug, you have a question?
Yeah, I have one question for Inti.
Yeah.
In your section about the charge and spin separation, what happens if you apply the magnetic field, in plane magnetic field to separate the energy?
In plane,
yeah,
like a Sodemann field. Yeah, exactly. So the formula is meant to be a formula that only depends on the shape of a Fermi surface, regardless of how that Fermi surface is sort of, how it's happening, right? So in a sense, what you will do with Sodemann is you will tune the shape of a Fermi surface, right? So the formula, is proportional to PF. There's a factor of 2 there that is just basically adding the 2 spins in the formula that I presented. So if you have then now 2 spins, 2 Fermi surfaces, one for spin up, one for spin down, that are different, then you will just, have the same formula for spin up and plus the formula for spin down. So you will be measuring PF, which it should lead to a change because it's not the area, right? So the area might be conserved, but
I mean, because of the chemical potential, the spin up and spin down are now different. So can you have something like spin current due to this different?
You will have, let's say, different areas for spin up and spin down with Sodemann, and then the formula will change. It will measure just the PF of the 2 Fermi surfaces.
Yeah.
But it's just this. We'll just measure the size of the Fermi surface, basically.
But I guess that's because of the change of the area of the Fermi surface, the value of the current will be changed if you apply electric field. So basically, in this case, maybe you will have the spin current. Because of the current of spin up and the current of spin down may be changed because of the different KF.
With Sodemann,
maybe it's not.
I don't see exactly, but this is a statement about the electrical conductivity, the net electrical conductivity.
Yeah, so basically, if you separate the spin Fermi surface by different KF, and then you apply electric field in, so you will drive both the spin up and the spin down electric current, but because of the different KF of the spin up and the spin down, maybe in total it will drive a net spin current.
Yeah, that would be, a very different situation, I would say, physically, but yeah, you could have spin currents in some way, but it would be different physics. I think, unless I'm missing something.
Okay, thank you.
Thanks.
Okay, we'll have time for one last question. Professor Haldane, you have a question? I think you're muted.
And how did you incorporate the curvature? Did you just, is it kind of you just decided PF was a curvature, or did you? How did you incorporate it into the dynamics? I mean, that was one issue that I spent a lot of time trying to think about when I was
right. So at the level of classical Landau Fermi liquid, it's just sort of the n, right? The normal. How is the normal changing with theta? You see what I mean? I could put the slides maybe just to make this
no,
more.
but did you actually manage to derive it in the dynamics, or you sort of you're just saying you put a PF in, and I mean, is it derived or just kind of intuitively guessed?
The theory.
I mean, yeah, you actually did it. You have, yeah.
Yeah, so the theory is just, you could view it just as classical Landau Fermi liquid theory. So
yeah, okay, but the classical one doesn't really incorporate the curvature. I mean, you need a.
Why do you mean that? Like I
mean,
I could just describe any shape of a Fermi surface, right? I just
No,
need
but
to
in the
do an
dynamic, I
expansion
mean, in the commutation relations, that's what I meant.
in the commutation relations, there is an n, right? A unit vector that is the normal to the Fermi
Yeah.
surface. So that's what I.
Yeah, but
what
you
changes
want something for the change, the gradient of n.
Oh, beyond the leading commutator, you mean?
Well, you're identifying stuff with the curvature, local curvature on the Fermi surface, right?
Yes.
You put a picture where you.
Yeah.
Yeah. I mean, did you actually derive that, or was that kind of just a sort of?
But, take Landau Fermi liquid theory, right? Classical. Okay. So that you can have curvature, right, for the Fermi surface.
Of course, but our question is whether incorporating it into the dynamics, did you identify, you put PF, and you would say identify PF as the radius of curvature of the Fermi surface.
I don't see exactly what you mean.
In your talk, you said you do a picture with a general shaped Fermi surface. And
let me make a very simple statement, right? So if you open Pines and Nozier's Fermi liquid theory, right? And you could have it for some Fermi surface that has an arbitrary shape, the equilibrium.
Of course you have a shape, but I question, okay.
This prediction of the transverse conductivity, you can just open Pines and Nozier's and do it with Pines and Nozier's. You don't need to do bosonization. And you will get the result. Actually, that result is in Pines and Nozier's. It's just that they were thinking about 3D. But you could just use classic Landau Fermi liquid theory and you will get that result that is independent of the Landau parameters.
But PF doesn't actually have a general meaning in an arbitrary shaped Fermi surface. If you're not,
yes, I see exactly what you mean.
Not a circus.
I see. I think I see what you mean. So you're thinking about the length of, like, where is the origin, so to say, where I measure PF as a radius, right?
Yeah, but there isn't such a, in general.
Exactly. No, very good. Yeah. I see now what you mean. So you don't need to make any reference to the length itself. It's something that comes out of the local curvature. So there's some information that's purely local of what is happening.
Yeah, I know the Fermi surface has a local curvature. The question is, I was just wondering how you managed to incorporate it in a consistent way.
Yeah, so let me try to I think I see more or less what you are concerned about. So let me try to say it slowly. So, in Landau Fermi liquid theory, there is some quasi-particle dispersion, epsilon of P, right? So this epsilon of P,
essentially the curvature is the relation between two close by points on the Fermi surface. But my just question was, I was wondering how you managed to get that into the, I mean.
Yeah, so there is some information which, it's completely determined by the behavior of the quasi-particle dispersion near the Fermi surface. You don't really need to know, stuff far away from what is happening to the quasi-particle dispersion near the Fermi surface. Because really this, what this response function is encoding is essentially the behavior of particle-hole pairs that are tangential to the Fermi surface. So it's like you remove a hole and you just put it, outside, almost tangential. So you
Because
just need
it's
information of
basically-
those particle hole pairs.
Okay, I'll look in your paper, but okay. It's not
you
enough.
know,
It was never, something I struggled with many
There is
times.
no, I sort of have a similar confusion. There is no information of the global radius in a sense. It's all determined by
Yeah, so the
local behavior
curvature,
of the quasi-particle dispersion in that.
local curvature is a
scene.
kind of cutoff on the transverse modes, and that's a difficult thing to see how to incorporate properly. Because, yeah, okay.
I mean, you know, Pines and Noziers, this result is in Pines and Noziers. It's just in 3D, and there is some universality in 3D as well. But it's classic Landau Fermi liquid theory.
Okay, I
Uh,
guess we have
but-
to move on. I don't know if we have extra minutes. Andre, do we need to move on to the next session?
Let's see. Do we have more questions?
I had a question.
Bert has a comment.
Okay, but if it's last question, let's quickly
So
do the
you're
question.
referring, you were saying that in Pines and Nozier, you have similar thing in 3 dimensions, but now in 3 dimensions, you would have 2 radius of curvatures. One dimension, I understand your formula, but I mean, 2 dimensions, I understand.
Yeah, yeah.
What happens in three dimensions?
Yeah, so in 3 dimensions, you know, the formula, just to be precise, so I think the formula that is listed in Pines and Noziers assumes a spherical Fermi surface. But I think there is a generalization to a Fermi surface with arbitrary shape, even in 3D, in which you end up measuring some kind of tangential perimeter. So you have a Q, that Q defines, you know, some direction, right? So when you try to go in 3D, you would map the points in the Fermi surface that you know, form some line, a closed line, that are tangential to that direction defined by Q. And then the formula reduces to something in which, you know, you take that length, more or less you make units of conductivity in 3D. So you need to divide, I think, by 1 over Q squared instead of like 1 over Q as here. But you get something that only knows about the shape of a Fermi surface. It doesn't know about the Landau parameters.
Thank you.
Yep.
Very nice work. Very nice.
Thank you. Thank you.
Okay, thank you to both the speakers. I guess we'll move on to the next session.